Molecular geometry is the 3D arrangement of a molecule's atoms in space. How are molecules arranged in space? Okay? And it means atoms within a particular molecule, right? We're not talking about how two molecules arrange themselves. We're talking about how atoms within a molecule arrange themselves. Okay? So in order to start looking at the shape of a molecule, we have to determine what are called the molecule's electron domains, or the central atom's electron domains. Okay? And so we look at the type and number of electron domains. I'm going to give you the definition of electron domains here in a second. But electron domains are very simple. Okay? Essentially, all electron domains mean is how many things surround the central atom. So I want you to really rewrite this. I don't really want our bonded to. How many things surround the central atom? Okay? We're going to be able to count electron domains by looking at that. Okay. So let's see. For example, if I gave you all right, so I'm going to look at this NH3 molecule. You don't have to draw this, but I want you to just look at it. If I'm looking at electron domains, how many things are surrounding my central atom? My answer would be 4. Right? I've got a bond, a bond, a bond, and a lone pair. This molecule would have 4 electron domains. Right? There are 4 things surrounding that atom. Okay? 4 things surrounding that atom. So, it's difficult for us to be able to determine an element's shape. It's 3-dimensional shape just by its structure. So we have to draw the Lewis structure to help us with that. Okay, so we're going to draw the Lewis structure, then we'll determine what does it look like in 3-dimensional space. Okay, so 4 domains here. If I were to give you CH4, how many electron domains would carbon have? 4. And they would all be what we would call bonding domains. Okay, on the NH3, it would be 3 bonding domains, 1 non-bonding domain. Okay, pretty simple, right? All right, I don't want that. So we're going to use this thing called, I call it VSEPR theory. I know that's really not how it's pronounced, but VSEPR theory gives us a way to determine a molecule's shape. It's 3-dimensional shape. Okay, and the acronym VSEPR, or VSEPR, you're going to have to know what that stands for. Okay, and what it means is Valence-Shell Electron-pair Repulsion. It's really fun. It's the most fun. Okay, once I explain what it means, it'll make sense, but it's a lot. Valence-Shell Electron-pair Repulsion. I'm going to give you kind of the book definition of it. You do not have to write down the book definition, but I'll give you a simplified one right after that. Okay? So you don't have to write this part down. I just want you to listen as I read through it. It says, the Valence-Shell electron-pair repulsion, it states, repulsion between sets of valence electrons surrounding an atom causes these sets to be oriented as far apart as possible. So all that means is that when we have electrons contained in an electron domain, they want to be far apart from other electrons, right? A negative and a negative repel each other. Do we agree with that? So this repulsion causes them to spread themselves out as much as possible. And that natural spreading causes these shapes of molecules. Okay? So the basis of electron repulsion theory is that electrons repel each other. They want to be as far apart as possible. You can write that down as kind of a basic definition of VSEPR theory, but it just means that our electrons want to spread out as much as possible. Okay, so that little basic definition I gave there is what you could have. You don't have to have that, but you do need to know what we use VSEPR theory for. Right? We use it to find 3-dimensional shapes. you do need to know that a non-bonding domain contains a lone pair and a bonding domain contains a bond. Right?
Wait, so it's used to find the structure of it?
Three-dimensional structures is what we use VSEPR theory for. Yep. Okay, and you'll have to be able to identify how many bonding domains and non-bonding domains we have. When we talk about bonding domains, we're really only looking at central atom. We don't care how many lone pairs an outer atom has, right? The central atom and its orientation of electrons determines the shape. Okay, that's really important. So maybe put that down here under electron domains, only for central atom. Wait, one more time. I would just put that along with the electron domains. So when we're looking at electron domains, we only care about the electron domains for the central atom. So we'll look at an example here, and I want you to identify domains. The example I have for you is water. So how many total domains does that oxygen atom have? It has 4 total domains. So how many bonding domains? 2. And how many non-bonding domains? 2. Right? 4 total, 2 lone pairs.
So every pair or bonds are domains?
Right. Every separate entity that is attached to the central atom is a domain. Okay. So we're going to just try one here. We're going to see how we can apply molecular geometry. You're going to need that handout I gave you. The backside of the Pauling scale is our molecular geometry kind of cheat sheet. You'll always get to use that. I'm not going to make you memorize molecular geometries. You'll get to use that. So I'm going to show you how to use that table based on a Lewis structure. So we're going to draw the Lewis structure for BCl3, and we're going to come up with the molecular geometry of that molecule. Okay, so BCl3. We're going to go ahead and find the actual Lewis structure for that. I think that contributes 3 plus 21, so 24 electrons. This one's really straightforward. And we should have lone pairs on each chlorine. Agreed? You'll see as you start to do these more and more, it'll come a lot quicker to you. You'll be able to see finished ones a lot quicker. So here's how we determine the geometry. We look at our central atom and we say, how many total domains does boron have? 3 domains. Okay, so I want you to look at that chart I gave you. You see how up on the left side there's a column that says total domains? Isn't that what that column says? Total electron domains. And we know boron has 3. And so you only have 2 options for the shape of this molecule. The shape could either be trigonal planar or it could be bent, right? Those are our only 2 options. So then we start looking at, and the next kind of column of our chart says, does it have a lone pair, right? Does our structure have a lone pair on our central atom? No. So you find the box where it meets 3 total domains, 0 lone pairs, which would be trigonal planar. Okay, does that make sense? Trigonal planar, it makes a triangle, and they are all in the same plane. Okay, each of these electron domains are 120 degrees apart. You see that angle is given to you there? 120 times 3 is 360, right? That's where those come from. We just make basically a little triangle. And they're always going to be in the same plane. They're going to tilt the same way. Next class, we're going to look at an app that allows us to manipulate molecules, so you'll be able to see it in 3 dimension, which I think will be helpful. But do you see how that chart works? Right? We find where the 2 meet. So it's total domains and then lone pairs. That's what you're looking at. You look at a molecular geometry for each central atom. So you have to look at, usually they'll have the same, but you'd say it's tetrahedral for each carbon or whatever it is. Okay? Let's look at another one. CBr4, I think, is our next one. CBr4. Let me fix something here real quick. So my Lewis structure here. If I would ask you for a real Lewis structure, you'd need the lone pairs on bromine. But if we're just trying to find the molecular geometry, you don't have to fill in the lone pairs. I think it's helpful. So how many total domains does carbon have? 4 domains. How many lone pairs? 0 lone pairs, which means what's the shape? Tetrahedral. Yep, tetrahedral. So tetrahedral molecules look something like this. You've got a 3 kind of pronged base with one that comes upward. So it almost looks like a tripod. That's what tetrahedral kind of looks like. We've got this tripod base, and then we've got one that pulls it upright, so it becomes 3-dimensional space that way. Again, you'll get to see that next class on an apps a little bit. Okay, what about NH3? I drew the structure for this just a little bit ago. And I think it looks something like that. So we need to count total domains first, which would be 1, 2, 3, 4. So 4 domains, 1 lone pair, which means good. Trigonal pyramid. Okay, when I learned them, I learned it as pyramidal. So if I say that, I'm not trying to throw you off. That's just how I learned it. Trigonal pyramidal is how I learned it, but either one is fine. Okay. These actually look the same as a tetrahedral molecule. It's shaped the same way. The only difference is that one has a lone pair, one doesn't. Okay, but realistically, they have the same angle of difference between those, right? Aren't they both 109.5? Right, so that means every set, right, these 2 sets of electrons are 109.5 degrees apart. Okay? Yes, a multiple bond only counts as 1 domain. So we're going to try a carbon dioxide molecule here, CO2. CO2. Do you guys agree with my Lewis structure? Is it the same as what you had? How many total domains do I have for carbon?
2.
I have 2 total domains. Do I have any lone pairs?
No.
Nope. So it means the shape or my molecular geometry has to be Linear. I want you to just think about that. If it's CO2, and I know my electrons want to be as far apart as possible, can we get farther apart than 180 degrees? No, right? They have to be in that straight line, right? It's just going to make this straight line thing. Same with if you would see just like an O2 molecule you needed to make one for. They just are bonded to each other. They can't orient themselves any other way than just a line, right? A single line. So sometimes you'll get asked for ones that have O2 when really you're like, well, which one's the central atom? How many bonding domains does it have? That's really a necessary point because the only way O2 could ever orient itself would be in a straight line, right? There's only 2 atoms, so it's linear. Okay, so I just wanted to kind of make that point there. Any other questions? Yeah. If I have multiple central atoms, I want to look at each carbon individually. So if I look at this first one, it's got 4 domains, no lone pairs. Tetrahedral. What about the second carbon? 4 domains, no lone pairs. What about the third carbon? 4 domains, no lone pairs. So you would answer this, you'd say tetrahedral for all carbons. Right? You just have to answer for each one. They have the same shape. You might get one that is a little bit different, but for the most part, you would be able to say that they were the same for all. But you do have to examine each central atom there. Okay? Great.